Good afternoon and welcome you back to this final session on this 3 days online workshop on design of experiments and engineering perspective. And in this session, we are going to see some of the basics of principal component analysis and how this principal component analysis is applied in an engineering experiment and how we are going to improve the information that is available in the data, or interpret how we are going to interpret the information available in the data. So the principal component analysis is generally known as PCA technique or PCA approach. So the idea of principal component analysis is to reduce the dimensionality of a data set. Okay, the data set may contain a large number of interrelated variables. That is, the variables which don't have interrelation with each other. So in this, what is by dimensionality? So the dimensionality refers to the attributes or features that the data set has. So how many features that the data set has, and that is called as the dimensionality. So we have to reduce these attributes so that obviously this dimensionality also gets decreased. Because whenever we are going to use more number of variables, this dimensionality of the features has to be reduced. So that is the main aim of this principal component analysis. Even though we are going to reduce the dimensionability of the data sets, the variation that present in the data set should be carefully retained, because based on that only we are going to analyze the effect of input parameters over the output parameters. So the variation that exists in the data set should be retained as much as possible. So how we are going to retain the variations? By transforming the variations or the variables by means of these principal components that are uncorrelated with each other. So the variation between the data sets can be retained by transforming to a new set of variables, and that is called as the principal components that are uncorrelated with each other. So here we can see an example. In the x-axis we have x1 and the y-axis we have x2. There are two variables. The relationship between two variables, or the relationship or data, the data variables or data sets that constitutes the relationship between these two variables is given in this plot. So now you can see the dimensionability. The dimensionability of this data set is very, very higher. So the variation is, the dimensionality of the attributes are higher. So by transforming these to a new set of variables, the variation we are going to retain. At the same time, the dimensionability is also being reduced. So we have to retain as much as the variation present between the variables, but at the same time we are going to reduce the dimensionality. So that is possible only with the principal components. So here you can see Z1 and Z2. So that is the principal components. So by making use of these principal components, the variation is retained, but at the same time the dimensionability has been reduced. So for this purpose only we are going with the principal component analysis in our study. So before going elaborate on the history or the why we need this principal component, first of all we see into some of the definitions of principal component analysis. So this principal component analysis is a orthogonal basis transformation. It's an orthogonal basis transformation in which the first principal components preserve the most of the variance that exists in the dataset. If I'm going to have three variables, then there exist three principal components. But among the three principal components, the first principal component holds or preserves the most of the variance among the datasets. So obviously we have to select the first principal component because the variation is retained or preserved in the first principal component. So initially this PCA determines the covariance matrix. The covariance matrix is nothing but the square matrix in which the variance exists. It's a square matrix in which the variance exists between the data sets. So the PCA initially determines the covariance matrix for the obtained data set, and from there it determines the eigenvalues and the eigenvectors of this covariance matrix. So the eigenvector is a non-zero vector. It's a non-zero vector, and the values that is associated with this eigenvector is known as eigenvalues. After determining the covariance matrix, this PCA selects the eigenvectors based on the values of eigenvalues. So the PCA selects the eigenvector that has the maximum value of eigenvalues in order to formulate the transformation matrix so that the dimensionality among the data set, the dimensionality in the data set can be reduced. It cannot be eliminated, but it can be reduced by selecting the eigenvectors based on the highest value of eigenvalue, highest value of eigenvalues. So the history of PCA. So the origin of this statistical technique. This is also a statistical technique. It is very hard to trace, but in 1873, Beltrami and Jordan derived a concept that is known as singular value decomposition. So singular value decomposition, which is normally known as SVD, which forms the basics for PCA. So this PCA is derived from singular value decomposition that is derived by Beltrami and Jordan in the year 1870s. Apart from that, Fisher, once again, he is the father of statistician, we call him like that. So he used this SVD in the agricultural trial. So day before yesterday, we have seen that the first field where this vision of experiment is implemented is in the agricultural field in order to improve the yield of the crop for some combinations of water quantity, sunshine, fertilizer, solid, then fertilizers, then soil conditions likewise. So he has also used this singular value decomposition process or technique in order to yield good crops. But the maximum usage of this principal component analysis was provided by Carl Pearson and Hartley in the years 1901 and 1933. So they make use of this principal component from the basics of singular value decompositions, and this technique is being used nowadays. So this principal component analysis is a multivariate problem. It's a multivariate problem, that is, we are going to use this for multivariable analysis. So the multivariable analysis, we have this factor analysis in which this PCA will be a part, but there is difference between this factor analysis and PCA. In a SPSS software and all these things, this principal component analysis will be under the title of factor analysis only. So now, what is the difference between this factor analysis and the principal component analysis? The major distinction or major variation among these two, the factor analysis and the principal component analysis, is there is a definite model in factor analysis, whereas in the case of PCA, no model is assumed. So in the PCA, no model is assumed, only the variance among the data sets is taken care of, and we are going to reduce the dimensionality aspects of the among the data sets. So no model is being used, but in the case of factor analysis, a definite model is developed, and based on that only the analysis will be carried out. Both the factor analysis and PCA uses the covariance matrix, but these principal components uses the data obtained from the diagonal elements, that is concentrate more on the diagonal elements. The covariance matrix is a square matrix. The covariance matrix is a square matrix. So this PCA concentrates only on the diagonal elements of the square matrix, whereas the factorial analysis is not interested in the diagonal elements, rather than it is interested in the off diagonal elements. It is interested in the rows and columns, but the diagonal elements it won't concentrate. But PCA mostly concentrates only on the diagonal elements. So this is the second comparison between this factor analysis and the principal component analysis. In principal component analysis, if the dimensionality of the model, consider M, the dimensionality of the model is increased from M1 to M2. That is, if I am going to increase the dimensionality of a data set from M1 to M2, then an additional principal component is included based on the variance among these two. Based on the variance among these two, another principal component will be included. And also the original M1, that is the first dimensionality of the model, are still present and it is unaffected. But in the case of factor analysis, when the dimensionality of a data set is increased from M1 to M2, it produces M2 factors, but it won't resemble the previous one. That is, from M1 only we are going to increase the dimensionality. So it forms another data set M2. The new data set will not resemble these older data sets. But in the case of principal component, the old data set dimensionality will be retained along with the principal component, which includes the variance among the old dimensionality and the new dimensionality data sets. So that's the another difference. So in the case of principal component analysis and factor analysis, in the principal component analysis or principal components can be calculated exactly from X, that is where it is being present, whereas the factor analysis cannot be typically calculated from the position. So X is nothing but the positions. So principal component analysis or principal components can be computed exactly from the variable X, whereas this factor analysis cannot be calculated. So steps in PC. The first step in PCA is developing the original multiple performance characteristics matrix. The x1 of 1, x2 of 1 up to xm of 1. It is the, for example, I am going to consider a L9 orthogonal array. So this x1 of 1, x2 of 1 and xm of 1 may be the output values that corresponds to flank pair. So 9 values that represent flank pair. So flank pair is considered as response 1. x1 of 2, x2 of 2 and xm of 2. Maybe it may be the output response 2, for example, surface roughness. So the surface roughness for trial number 1, x1 of 2, the surface roughness for x1 of 2, x2 of 2. Similarly, we have to formulate this in a matrix form. So where xi of j represents the value in the matrix. So in our study, we are going to determine the principal components and then we are going to include that in the Gray relational analysis. So this x1 of 1 may be the Gray relation coefficient of the first response and x1 of 2 may be the Gray relation coefficient of response 2 and similarly like that. Where m is the number of experiments. As told, if I am going to have 9 experiments, then m is equal to 9. The n is the number of outputs. For example, if I am going to have 3 outputs, then x1 of 3. So x1 of 1, x1 of 2 and x1 of 3. So 3 outputs I am going to put it in a matrix form. The second step is formulating or correlating the coefficient array. The coefficient array. So the covariance that exists between xi of j and xi of L is the covariation of sequences and sigma is the standard deviations of sequence j and then sequence L. So this correlation matrix we have to determine so that we can find out the principal components. The third step is determination of eigenvalues and eigenvectors. So determining the eigenvalues and eigenvectors. So the eigenvalues and eigenvectors are determined from the correlation coefficient array that we have seen previously. So from there only we are going to determine the eigenvectors. The eigenvector is of a linear transformation, is a non-zero vector. The values that corresponds to this eigenvector are known as eigenvalues. So from the correlation coefficient array, we are going to determine these eigenvalues and eigenvectors. Then from this, we are going to calculate the principal components. After determining the eigenvectors and eigenvalues, we are going to determine the principal components and the uncorrelated principal components, because our ultimate aim is to determine the uncorrelated principal components so that the dimensionability may be reduced among the data sets. So we are going to reduce the dimensionability. For this only we are going to determine the uncorrelated principal components. So by using this formula we are going to determine. So ym of 1 is known as the first principal component and ym of 2 is called as the second principal component and so on. So ymk is the general form. So that is how many outputs we have or how many inputs we have. Based on that, the principal components will be developed. If I have 3 inputs, then obviously 3 principal components will be formulated or developed. But the maximum variance will be preserved only in the first principal component. So we have to select only the first principal component. So these principal components are aligned in descending order. That is, The first principal component will have a higher value, that is, most of the variance is preserved by the principal component 1. Then comes the principal component 2, whereas least or somewhat lower variance will be preserved by the principal component 2 than that of the principal component 1 and principal component 3 and so on. So what are the various plots that we can obtain during the principal component analysis? The first one is the scree plot, the second one is the score plot, and third one is the loading plot, and fourth one is the biplot, then outlier plot. So one by one we'll see the different types of plots that is available or that can be drawn during this principal component analysis. So here comes this scree plot. The scree plot displays the number of principal components versus the corresponding eigenvalues. So component number, what is its eigenvalue? So here in this case, in this image, we have 8 components. Principal component 1, principal component 2, principal component 3 up to principal component 8. The eigenvalue of principal component 1 will be around 3.6. So the principal components are arranged in the descending order. So the eigenvalue 3.6 formulates the principal component 1, and a lower one will be the principal component 2, and lower one will be principal component 3 likewise. So the eigenvalues of the correlation matrix equals the variances of the principal component. So how much variance that exists among the principal component, that will be provided through these eigenvalues. So from this scree plot, what we are going to interpret? So based on the eigenvalues, which principal component that we have to use, that can be identified by this scree plot. So here the principal component 1 has a higher eigenvalue, so that can be used. Then comes the score plot. The score plot is a graph that is drawn between two principal components, that is the second principal component and the first principal component. So how much variance that exists between these two principal components. So this is some example how a principal component is, how a score plot is drawn between first and second principal component. So this is particularly useful to assess or identify or to interpret the type of data set, the clusters that we are going to detect, whether all the data are placed in a particular place, that is called as clusters, outliers, whether there is any much deviations, and a trend we can also identify from this score plot. So why we have to draw only between these two? That is, this score plot can be drawn only between the first component and the second component of principal component analysis. That is, first principal component and second principal component. Why can't we take third principal component? Why can't we draw it between principal component 1 and principal component 2, or in between principal component 2 and principal component 3? Why can't we? As told, the most of the variance is preserved only in the first principal component, and a least and somewhat lower variance is held in the principal component 2, as most of the variance are preserved by these two principal components. So the score plot is drawn only for these two principal components, which holds much of the variance among the data sets, much of the variance in the data. That's why we have to go with principal component 1 and principal component 2. Then comes the loading plot. this loading plot plots the coefficient of each variable for the first component versus the coefficient for the second component. That is the first principal component and the second principal component. So for example, if I am going to consider three inputs, then number of variable is 3. So in first principal component, for these 3 inputs or for these 3 variables, I will be having a coefficient. Similarly, in principal component 2, for these 3 input variables, that is flank wear, surface roughness, material removal rate. These are the 3 variables. For the 3 variables, I will be having a coefficient in principal component 1 and also in principal component 2. So these coefficients are being correlated using this loading plot. So here you can see the first component and second component. So the coefficient of each and every variables is being plotted. So from this, what we are going to interpret? So from this, we are going to determine which variable is having the largest effect on each component. Among the 3, the flank wear, surface roughness and material removal rate, which is going to have a higher influence, that we are going to identify from this. So here we can see these loading plots can be drawn between -1 to +1. These loading plots are normally drawn between -1 to +1, and the variables or loadings that are close to -1 or +1, that is the ranges, the lower range and upper range. So the loadings of variables, that is variables that are placed nearer to -1 and +1, largely influences the component. The component is nothing but the first principal component or the second principal component. So that variable that we can identify. So the loadings that are nearer to 1 or 0, the loadings that are nearer to 0 have weak influence. In this image, you can see the debit and credit cards are placed very nearer to 0. So the influence of these 2 variables are very, very weak. So we can omit those 2. But look at the other one, age, residence, then employment, and all these things are placed above nearer to 0.5. So their influence will be higher. Then comes the biplot. The biplot is nothing but combining the score plot and loading plot in one plot. So here you can see. So loading plot is drawn between -1 to +1, and then this score plot is used to determine the outliers, the clusters, like this. So these 2 things we are going to combine. So these biplots are specifically useful in identifying the data structures and the loadings of the first 2 components in a single graph. So for 2 different graphs, I am going to merge and I am going to present it in a single graph. Then outlier plots. So these outlier plots displays the Magalomit's distance for each observation and a reference line to identify the outliers. So it displays the Magalomit's distance for each observation. That is for, if I am going with the 9 observations, means for each observations it is going to display the Magalomit's distance and with reference to a reference line. Because based on that only we are going to determine how much these data are going to be the outlier. Outlier means that exits the reference line. The Magalomit's distance is the distance between each data point and the centroid of the multivariate space or the overall mean. So from the overall mean, how each data point is varying or how much distance each data point is positioned, that we are going to determine by means of Magalomit's distance. So the main purpose of this Macaronis distance is to identify the outliers. So this is the plot. So here you can see the reference line is 4.4, but all the points are within the reference line, so there is no outliers. So there is no outliers at all. So coming up with this, we come to the end of the PCA presentation. So with this, we come to the end of the PCA presentation. And now we are going to look into one case study, how to incorporate this principal component analysis in our optimization problem. And then we'll see a hands-on training session on this principal component analysis. So here I have taken 4 parameters varied through 4 levels. In this case, 3 parameters are numerical and 1 parameter is categorical. The tool coating material is categorical because I am going to select the type of coating material: titanium aluminum nitride, titanium carbon nitride, and titanium nitride, and uncoated. So these are the coating materials that we are going to use. So for this, based on Taguchi's approach, I am going to select a L16 orthogonal array for 4 parameters varied through 4 level arrays. So I have formulated the L16 orthogonal array. So the last 2 is missing. Now you can clearly. So number of trials is 16. So cutting speed, feed rate, depth of cut, and tool coating material. So based on this, experiments were conducted, and then the outputs were recorded. And then we are going to determine the gray relational coefficient. We are going to determine the gray relational coefficient as per the gray relation approach technique, and then I am going to incorporate this principal component in this, so that I am going to determine the MRPI. The MRPI is nothing but multi-response performance index. So during the principal component analysis, these 3 components we have obtained, because here the number of outputs is 3: the wear, roughness, and material removal rate. So 3 components I am going to have: the component 1, component 2, and component 3. So for this, the eigenvalues is 1.689, 0.989, 0.322. So the first principal component with the highest eigenvalue has to be selected. Here you can see the eigenvector that corresponds to the principal component 1 is selected for our analysis. Now what is the variance, the difference between these two? The difference between 1.689 and 0.989 is 0.7. The difference between 0.989 and 0.322 is 0.667. So how much percentage variation that exists between these two? So these things it will, so here test with total, and that we are going to divide this by this. So that will give us the percentage of variations. Then I am going to cumulative, means that I am going to add. So this is 56.289. So cumulative is also 56.289. Then add this with this total, the percentage variation. Then it becomes 89.27. This 56.289 plus 32.970 will formulate this cumulative percentage. Now adding this with this will be 100%. So we have to select the component that has the highest eigenvalue. Okay. So here the principal component 1 has the highest eigenvalue. So I am going to select this eigenvector. So 0.560, 0.704 minus 0.436. So this is for flank wear, because my outputs is wear, roughness, MRR. So the first one is for flank wear, the second one is for surface roughness, and the third one is for material removal rate. Now, how this principal component is derived and on what aspects this multi-response performance index is arrived. So here you can see the gray relation coefficient is 0.909, 1 and 0.333. This value I have taken this value 0.909, 1, 0.333. So now 0.909, in order to calculate this principal components for VR, the gray relation coefficient value 0.909 into, here come to the eigenvector value for Frank VR. It is 0.56 square of this term. So 0.909 into 0.56 the whole square will produce you 0.288. Will produce you 0.288. So here it is clear now. So here is equal to 0.909 into 0.56 the whole square. Here for surface roughness, the eigenvector is for component 1 is 0.704. So the gray relation coefficient for roughness is 1. So 1 into 0.704 the whole square, so it is equal to 0.496. Similarly for MRR, the eigenvector is minus 0.436. Since we are going to square, the minus will also become plus. So 0.333 into 0.436 square, that is 0.063. In order to determine the multi-response performance index, we are just going to add these three MRPI, these three principal components, so that I can end up with this 0.847. So here you can see the MRPI for first experimental trial is 0.847. So this is how we are going to calculate. So after calculating this MRPI, again I am going to determine the main effects plot. I am going to determine the main effects plot by entering the values of input parameters and the MRPI values in Minitab. So we have to go with the stat ANOVA main effects plot, so that I can determine the main effects plot. Then I can determine the interaction plot, and also I can determine the ANOVA table. So where comes this? What is the use of this? So previously we are going to provide some weightages. Someone is asking on what basis these weightages are given. It's purely given from our experience. This 0.5, 0.3, 0.2. But depending upon the variance that exists among the data, these principal component produces these eigenvectors. So by incorporating these eigenvectors as weightages, a perfect model can be developed. A perfect model can be developed for interpreting the data. So this is the ultimate aim of carrying out this principal component. So this is the ultimate aim of carrying out this principal component. I hope now everyone is clear. So during this principal component component analysis, we can have these data. We can have these plots. The first plot is the score plot, in which we are going to, so that is the loading plot. First one is the loading plot, in which we are going to plot the data in between -1 to +1. So here in +1, the surface roughness is located. In +1, the surface roughness is located, and around 0.7, the flank wear is located, and among 0.55, the MRR is located. So the influence of surface roughness is high, as it is located among the extreme end of 1. The second one is the score plot. The second one is the score plot, where we can identify the outliers and clusters and data structures. So there is no, there is no clusters, but observation 6 is far enough. But the remaining data sets are located randomly near the axis itself. So by combining these two plots, by combining this loading plot and score plot, I am going to draw the biplots. So here you can see the position of this flank wear, MRR and surface roughness, and the 16 readings. But that is also within the outlier. It is not an outlier, it is within that reference line. So from this we are going to determine the data structures, clusters, outliers, so whether our data are perfect or not. So by using these plots, we can easily identify. I hope this presentation is informative to you, and with this I come to this end, and now I will solve two problems. I will solve two problems in principal component analysis using Minitab software. So now I am going to select this. So the first example is this L16 orthogonal array. Right. Now I delete these two. Now I will delete these two. So now you know, in gray relational analysis, the final step is to determine the gray relational grade, and before that we will be determining gray relational coefficient. By averaging the gray relational coefficient, we are going to determine the gray relational grade. So instead of that average, that is 33.33% of importance to every output in this case, we are going to give some weightages based on the principal components. Just to copy this, the gray relation coefficient that I am going to copy, and I am going to paste it in the Minitab. Just I am going to paste it in the Minitab. So this is the gray relational grade of wear, roughness and MRR. Now go to stat, multivariate analysis. In this we have both the principal component analysis as well as the factor analysis. So here also you can see by symbol. So this principal component analysis concentrates more on the diagonal of the square matrix, whereas the factor analysis, it is more concentrated on the off diagonal elements. So principal components. So the variable is, these three are my variables. That is my inputs. So how many inputs? 3 inputs. So number of components to compute, that is 3. So in this graph, we can just click the graphs, we can see these 5 graphs. Just click what are the graphs that we require. What are the graphs that we require? Okay, and storage, just leave as it is. Click OK. So this is the, I will tell you one by one. The first plot is my scree plot. The scree plot is drawn based on the principal components and the eigenvalues. So it is a descending order. It will be positioned in the descending order. Here we have carried out 3 variables. We have performed the analysis on 3 variables, VR, roughness and MRR. So 3 components is produced. So the first component has an eigenvalue of 1 point nearly to 1.7. So it is 1.69. On the right here you can see. So eigenvalue is 1.6922. And this is the second. Its component is 0.98. So here you can see this 98. Here you can see, and the third one is 0.32. So here you can click. The third one is 0.32. This is principal component 3. So most of the variance exists between these two, principal component 1 and the principal component 2. And this is the outlier plot, whether any one of the observation is going out. So the reference line is set as 3.326. This point is nothing but row number 16. So in our presentation also we have seen that is extremely over, where the other data are positioned in a random manner, but this is the outlier. So the reason for this outlier we have to determine, or if there is any problem with the experiment, we have to perform another experiment for trial number 16. So this 16, experiment number 16 value is an outlier value that has to be corrected. So from this we can determine the data which is the outlier one. So this is the score plot which is drawn between the first component and the second component. So the data structures, clustering, everything can be observed. So no clustering of data is seen. So here you can see the loading plot is drawn between -1 to +1. -1 to +1. The variables that are present nearby -1 or nearby +1 will have higher influential value. The variables that are present around 0 have least influence. So in this case, the influence of surface roughness is higher, then the wear is higher, and then the MRR is higher. The MRR is close to 0.5. It is close. The wear is close to 0.6, and roughness is 0.7. So this is the biplot in which we are going to combine both the loading plot as well as the scree plot. So here you can see. So in this example, you can see that this example you can see the eigenvalue. The eigenvalue for first component is 1.6922. So this value 0.9841, 0.3237. So the difference, the proportionate is 5.6. So the difference we can calculate. So the percentage of variation, the proportionate 56.4. So 56.4, then 32.8 and 10.8. That we can see here, the proportion. Here you can see the proportion is 0.564. That is 56.4. That is the percentage of variation. This is. Then comes the cumulative. Just add these two. This 0.564, then 0.564 plus 0.328 will be 0.892. Then 0.892 plus 0.108 is going to be 1. So that is the cumulative percentage. So coming below this, we have these variables. So principal component 1, principal component 2, principal component 3. That we are going to record it here. So this is the principal components. For component 1,
The variable VR is 0.561. The weightage is 0.561, 0.703, 0.437.
Then this is for principal component 2 and this is principal component 3. So which principal component we have to use? That is mainly dependent upon this eigenvalue. Mainly depend upon the eigenvalue. The eigenvalue is larger for principal component analysis because the principal component analysis one preserves most of the variance among the data. So kindly select that principal component. That's why I am going to select this value. I'm going to select this value. Okay. Now, how to work on this? So, for VR, my value is 0.561 for VN. 0.561. 0.561 for roughness. 0.703. For MRR, 0.437 minus 0.437. So, which is equal to?
It is equal to, I'm going for the formula, this VR into
this principal component, that is 0.561 square, or just put another star 0.561. I am squaring this principal component so that I am going to provide the weightage. Similarly for roughness, which is equal to this roughness into 0.703 is the eigenvalue for the eigenvector value for this 0.703.
Similarly for MRR, which is equal to the gradation coefficient for MRR into, so once we are going to square the minus, it becomes positive. So just to take the positive term alone, 0.437 into 0.437.
So just copy these three and just paste. For MRPI, just add these three. I'm going to add these three. Plus.
Why we have to add? That's a big question. Why we have to add?
Because here you can see the cumulative is 100. The cumulative is 100. That's why we are going for this addition. Just to copy this. So we know the input. For this. So this is my input data. So this is my input data. So now I am going to copy this input data and then I am going to paste here. So file, new project. Just I am going to paste. Then MRPI, or I will do it in the full multi-response performance index. Multi-response performance index is this value, or take it for 3 digits. The number of digits is 3. And now paste it here. Now I'm going to draw the main effects plot, and then I'm going to draw the interaction plot,
and then I'm going to develop
or formulate on our table. So stat DOE Taguchi, directly don't go for Taguchi, sorry, ANOVA, main effects plot, response is multi-response performance index, then factor is this 4, select. Okay. Now here you can see. So this is my, so how to derive optimum condition? So this is the larger one. So if two are same, so 6419, 6431. So this is my optimum condition. There is 253 of cutting speed and feed rate, and this is the depth of cut is 0.4, and the tool coating material is titanium aluminum nitride. So by using this, I can obtain lower tool wear, lower surface roughness, but higher material removal rate. Then stat, ANOVA, interaction plot. The response is multi-response performance index. Then 4 inputs, full display. So here you can see, apart from this, there is a significant interaction. Apart from these two things, between feed rate and tool coating material, depth of cut, and even though depth of cut and tool coating material have a little bit of interaction, between feed rate and coating material does not have any influence at all, because more or less it is parallel lines. Then go for ANOVA, stat, ANOVA, general linear model, fit general linear model. The response is multi-response performance index. Then factors are the 4 inputs. Let's do this. Check for the R square value. We have to check the regression coefficient, that is 97.56. So it is a valid model.
So here today we have seen this principal component along with an example. Now I will work on another example
That we have provided in the morning. So this is the morning template that we have developed for gray relational analysis. So instead of this gray relation grade, I will have this gray relation grade as it is, and now we are going with the principal component analysis for this.
or principal component analysis, and then I have my MRP.
So gray relation coefficient I am going to consider, just to take this. So just gray relation coefficient I am going to consider, because from this only I am going to calculate the principal component analysis.
So 9 experiments. So stat, multivariate,
Principal components. The variables is 2. So 2 variables. So number of components to compute is 2. Graphs we require. What are the graphs we require? Okay. And okay. So here you can have the eigenvalue is 1.6595 for principal component 1. For component 2 it is 0.34. So proportionate 83%, then
0.17. So cumulative is 100. So eigenvalues for principal component 1, the tensile strength is 0.707, hardness is 0.707. So equal weightage only it is going to provide. So this is 0.707 and this is also 0.707. So which is equal to this tensile strength into 0.707 into 0.707, because we have to square the principal component term. It is equal to this hardness into 0.707, 0.707. It is equal to this plus this. We can have the same value now. So kindly check these two values. It is more or less similar. Why it is more or less similar? Because the two principal component is 0.707 and 0.707. Since the same value exists, so 50% weightages the principal component. So in this case, even though we implement analysis, there is no difference. So the 50% that we have selected, weightage that we have selected for our analysis itself is good. Itself is good. So with this, we conclude today's session and hope you all had enjoyed this 3 days workshop, and also you have learned something from this hands-on training, and I wish you all for your future success in your career. Thank you. Now I will be coming to chat. If you have any doubts, you can chat with me and you can get it clarified. Thank you.